Okay, so our next step, let's move on to our other forms of numbers. Fractions are where we really need to spend some time because most people struggle with those. We mentioned when we add fractions, we have to have a same name, and that becomes that common denominator. So if I have something like 2/3 plus 1/4, we can't add those the way they are because they currently have different names, thirds and fourths. So we need to figure out what that common name is going to be, and we need to change them. Also, the first thing we need to figure out is how do we rename fractions? To figure that out, we need to understand how fractions work. 3/4. Easiest way to think of that is to go back to the old grade school illustration of the pie or the pizza. The denominator, the 4, the name of 4 means that every whole object is cut into 4 equal pieces. Or you can think of it the other side, it takes 4 pieces to make one whole object. The 3 means that we have 3 of those pieces. So 3/4 means we have 3 out of the 4 pieces required to make one whole thing. Renaming that, one of the things we could do is we just cut each of those pieces in half. Well, now how many pieces are there? 8. And how many do we have? Well, 6. By cutting each of them into 2 equal pieces, we just multiplied each of those numbers by 2. 3 times 2 and 4 times 2. So we can multiply the top and bottom of a fraction by the same number, and it won't change the value. It just changes its appearance. So the key is to figure out what it is we're going to multiply by. For example, if we have 2/5, and I want to change it to 30ths, what do I have to multiply 5 by to turn it into 30? 6. 5 times 6 makes 30. So I have to multiply the top by the same thing. 2 times 6 is 12. And the reason we have to do that, remember, is we're cutting every piece into 6 equal pieces. We can go the other way as well. 12/20ths, if we can multiply the top and bottom by the same thing, we can reverse that. We can divide the top and bottom by the same thing. What can both of those be divided by? 4. 12 divided by 4 is 3. 20 divided by 4 is 5. 3/5. What if you didn't see that 4 that we could divide by? What if you just said, well, they're both even, we'll divide by 2? Well, you divide by 2, you get 6/10, and then you can see you can divide by 2 again. You get 3/5. So you're going to get there, it's just going to take a few more steps. So for now, let's take a look at that. First thing we need to figure out is what name we're going to change both of those to. We need to know what number both 3 and 4 can go into. We can always make lists. If you count up by 3s, you got 3, 6, 9, 12, 15, and so on. Counting up by 4s, it'd be 4, 8, 12. There's our match. 12 is the one number that the smallest number that both of them can go into. You don't have to have the smallest number. In fact, you can always just take the two of them and multiply them together. 3 times 4 would make 12, which in this case is the smallest denominator. Sometimes it won't be, but it'll still work. So anyway, how do we turn a 3 into a 12? Times 4. So you have to do the top by 4 as well. 2 times 4 is 8. So 2/3 becomes 8/12. How do we turn the 4 into a 12? Times 3. So 1 times 3 is 3. So 1/4 is the same as 3/12. And then we're going to just add 8 and 3 makes 11. And we keep the same name, 12ths. Well, what happens if we get something like this? Where the numerator is bigger than the denominator. This is telling us there's enough pieces to make at least one whole object. In this case, I can take 8 out of 15 once with 7 left over. So that's one whole object, and there's still 7 of those 8s left over. I might have like 47 7ths. How do I figure out how many whole objects and how many leftover pieces I have? Well, if you use your calculator, you do 47 divided by 7 would be 6.714285714 approximately. What's that tell us? I have too much time on my hands, for one. There's 6 whole objects in there, and there's some pieces left over. What's 6 times 7? 42. Which means you used up 42 pieces, there are 5 left over. That's basically just a division and a remainder. 47 divided by 7. 7 goes into 47 6 times. 6 times 7 is 42. There's 5 left over. So it's 5 sevens. Make sense?
You just don't remember what 5 sevens was? Or...
Math is about patterns. And once you see the patterns, the calculations are really, really simple. I've been doing this every day of my life for, oh man, I don't want to think that far back, for like 19 years now. I've recognized a lot of the patterns. And once you, like I said, once you see them, once you realize that that's what you should be looking for and you start to see them, the calculations are really simple. I could keep going with the 4 sevenths for probably 40 or 50 digits if you wanted me to. Try me sometime. I'm really fun at parties. Anyway, so we can do that, or we could take something like 2 3/5. This is what we call a mixed number. And we can convert it back into something like this, which is what we called an improper fraction. Now, there's nothing improper about it or incorrect about it. They just call it an improper fraction because we don't like having the numerator bigger than the denominator. But there are cases where it's easier to have it that way. So to do that, I got to figure out how many pieces are in these 2 whole objects. Well, the 5 tells us that. Each of them has 5 pieces. So that's a total of how many? Well, 2 times 5 is 10. Plus, there's already 3 pieces there. 3 plus 10 is 13 fifths. So I have 7 1/8. 7 times 8 is 56. Plus the 1 is 57 eighths. Notice this denominator never changes. That's still eighths. This here is fifths. It's still fifths. Up here it was sevenths. It's still sevenths. That denominator never changes when we do that. So we can add fractions like 5 6 3/4. What's our common denominator going to be? 12 again. What's this going to become? 10 twelfths, and this will be 9. So we add 10 and 9 makes 17 twelfths. What's wrong with that? It's a mixed or improper fraction. So we can get 1 and 19. I'm sorry. That's what's wrong with this. I didn't. Sorry. It's 19 twelfths, so it's going to be 1 and 7 twelfths. Sorry about that. It's late at night. The little hamster refuses to get on the wheel anymore after 5 o'clock. Any questions? Well, enough of dealing with simple fractions. Let's jump up to mixed numbers. Oh, let's see. Let's do something like this. Notice when I set up my mixed numbers, I line up the digits of the numbers, then I just line up the fraction at the end, just like it's the last digit. Because that's really all the fraction is the last digit at the end of the number. Now we still need a common denominator, so I'm going to rewrite the whole number, and we're going to change the fraction. What's our common denominator going to be? 20. We could have just done 4 times 10 and got 40. That would work. We just have to reduce when we were done. 20 is our smallest one. What do we have to do to the 4? Times 5, so 1 times 5 is 5. This is going to become 18. And now, just like whole numbers, we said we're going to treat that fraction as the last digit. We're going to start on the right, work our way back to the left. 5 and 18 is 23 twentieths. Well, that is 1 and 3 twentieths. So still, just like whole numbers, we're going to keep part of it, 3 twentieths, and we're going to carry part of it, the 1. 1 and 3 is 4, plus 5 is 9. So 9 and 3 twentieths. Make sense? Subtraction of fractions is pretty much the same. We're going to jump right into mixed numbers for subtraction. Do something like 8 2/3 minus 4 4 4/5. Just like with addition, we need a common denominator. In this case, it's going to be 15. This is going to be 10, and this will be 12. But we are subtracting now. 10 minus 12, however, can't be done. So we're going to, just like with whole numbers, we're going to borrow from the 8. This is going to be a 7. What's this become? 25. Yeah, what we borrowed here was one whole object. That 15 tells us that that one object has 15 pieces in it. So we have 10 plus 15 more pieces. There's 25 of those 15ths. So now we subtract. 25 minus 12 is 13 15ths. 7 minus 4 is 3. Let's do at least one more example of that. So 284 1/4 minus 197 and 5/8. So the 284 doesn't change, the 197 doesn't. Notice I'm still lining up the digits. What's your common denominator going to be? 8. So the 5/8 doesn't change. The 1/4 becomes 2/8. Well, again, 2 minus 5 can't be done, so we're going to borrow from the 4. That'll be a 3. This will become, what do we add to the 2? We have to add the 8, the denominator. That makes it 10/8. So it is now 10 minus 5 is 5/8. 3 minus 7, well, we're going to borrow just like other whole numbers. 13 minus 7 is 6. 7 minus 9, borrowing again. 17 minus 9 is 8. 1 minus 1 is done. So 86 and 5/8. Good stuff, right? For those of you wondering, am I ever going to make you do a test or a quiz without a calculator? No, I won't. And yes, most of your calculators, including the TI-30 that I recommended, has a fraction button on it. If you get one and you want to learn how to use it, let me know sometime and I'll show you either outside of class or at the beginning of class next week. Let's multiply fractions. As we said, you're just going to multiply straight across because you combine counts. 2 times 3 is 6. Then you also combine names. 5 times 4 is 20. What do we notice about that answer? Can be reduced by 2, giving us 3/10. Some of you might be thinking, why didn't he cross cancel? Others at this point might be wondering, what's cross canceling? Well, because this is going to become 2 times 3 over 5 times 4. You can see here that both the 2 and the 4 can be divided by 2. So rather than multiplying it out and reducing later, you can actually reduce before we divide. So I could take the 2 and the 4 and divide them both by 2 to make it 1 and 2. Now 1 times 3 is 3. 5 times 2 is 10. The answer I get is already reduced. Now in a problem like this, it's just as much work to cross cancel as it is to reduce when you're done. But you can run into problems like this, 24 25ths times 35 36. And doing a problem like that, you're going to end up with something like 840 over 900 and have to reduce it. Well, to me, it'd be easier to cross cancel first. I look at this, the 24 and the 36 can both be divided by 4, 6, and 12. Give us 2 and 3. 25 and 35 can be divided by 5 to give me 5 and 7. So now 2 times 7 is 14. 5 times 3 is 15. 840 over 900 would reduce to 14/15. It'd just take a little work. Enough talking about simple fractions. Let's jump up to the mixed numbers again. Let's do 5 and 1/3 times 7 and we'll do 1/4. Multiplying mixed numbers is actually a really tough process. In fact, you go to the university over here and pick 100 people. I'd be shocked if even one of them, including some of the math professors, could show you how to multiply mixed numbers correctly. So the answer to how do you do it is, we try to avoid it. How do we avoid it? We turn them into improper fractions. 5/3 is going to become how many thirds? Or 5 1/3 is going to become how many thirds? Yeah, 5 times 3 is 15, plus 1 is 16. 7 1/4 will become how many fourths? 29. Good. 7 times 4 is 28, plus 1 is 29. Now you can still cross cancel. You can see here that the 16 and 4 can be divided by 4 to give me 1 and 4. 29 times 4 is 116. 3 times 1 is 3. 116 divided by 3 is 38 and 2/3. Just for the fun of it, let's show you how to do the mixed numbers. Don't write this down. I will never make you do this. I'm just showing you so you can appreciate that whole idea of making them into improper fractions. This is based on the same concept as like 24 times 35. Not only do you have to do the 5 times 4, but you have to do the 5 times 2 as well. Same over here. You have to do 1/4 times 1/3, which is going to give us 1/12. But you also have to do 1/4 times 5. How do you multiply a fraction by a whole number? Make it 5 over 1. Make it a fraction. That's 5/4 or 1 1/4. Now I have to do the 7 times 1/3. So again, that's 7 over 1 times 1 over 3. 7/3 or 2 1/3. And then 7 times 5 is 35. Now we need a common denominator. Looks like it's going to be 12. So that's 1/12, 3/12, 4/12. 1, 3, and 4 is 8/12. Or, reducing to 2/3. 1 and 2 is 3, plus 5 is 8, and 3, 38 and 2/3. We get the same answer. I think I'll stick to this. But again, I just wanted to show you, again, there's not just one way to do each math process. Let's do another one. 12 3/5 times 2 4/7. Tell me what to do. 5 times 12 is 60, plus 3 is 63. Good. 2 times 7 is 14, plus 4 is 18/7. Then what? Can we cross cancel? Say yes. Okay, what can we cross cancel? 63 and the 7. Both can be divided by 7, giving me 1 and 9. 9 times 18, you guys all know that's 162. 5 times 1 is 5. 162 divided by 5 is 32 with 2 left over. Long division. 5 goes into 16 3 times. That's 1, bring down the 2. 5 goes into 12 twice. That's 10, there's 2 left over. Questions? Okay. Division of fractions is where the fun starts. Just like the long division with whole numbers, division with fractions is another one that's been changed to the point where you cannot recognize it anymore. I have 12 25ths divided by 4/5. When we multiplied fractions, we just multiplied straight across, didn't we? We said division follows the same rule, so can we divide straight across? Can I look at this and just do, where'd it go? 12 divided by 4 is 3, and 25 divided by 5 is 5. Does that work? Is that the right answer? Actually, it is. Would it work every time? Yeah, it would. Why don't we do it that way? Because math teachers are mean and they want us to suffer? Well, no. That's only part of it, by the way. We run into problems like this. 3/4 divided by 2/3. Well, 3 divided by 2 is 1.5. It doesn't work out evenly. Same with 4 divided by 3. It doesn't work out nice. What have we been taught to do with problems like this? We don't divide, we multiply. It becomes 3/4 times, we use that fancy word called the reciprocal. You flip this over, times 3 over 2. 3 times 3 is 9. 4 times 2 is 8. 9/8 or 1 1/8. Believe it or not, this here, this multiplying by the reciprocal, came from this. Let me show you how. Once upon a time, in a land far, far away, the way we would have divided fractions would have looked like this. Come on. 3/4 divided by 2/3. We would have looked at this and said, hey, 2 times 3 is 6. So we're going to rename this by multiplying by 6. 3 times 6 is 18. 4 times 6 is 24. 18 divided by 2 is 9. 24 divided by 3 is 8. It's 9 eighths, or 1 1/8. That's the answer. So you might be saying, oh, he said that this came from that. How? Well, at some point, somebody was doing this and they realized that right here, whenever you did, if you took, let me write this out again, 3/4 times the 6/6 divided by 2/3. If you took this part here and did it first, 6 divided by 2 is 3. 6 divided by 3 is 2. That what you get there is always just this fraction flipped over. And then it's multiplying. So they gave it that fancy name of reciprocal and then defined multiplication or division to be multiplication by that reciprocal. So all that reciprocal is doing is taking out a whole bunch of these steps. It's a shortcut. So anyway, let's jump up to doing some division with mixed numbers. So, since we've already decided we're going to turn division into multiplication, if we're going to divide mixed numbers, it makes sense that we're going to do it just like we do with multiplication, and we're going to turn them into improper fractions. So 5 1/3 becomes how many thirds? 16. 5 times 3 is 15, plus 1 is 16. 2 3/5 will become 13/5. Is this multiplication now? No. Still division. What do we have to do to make a multiplication? Take the reciprocal. This becomes 5/13. So now 16 times 5 is 80. 3 times 13 is 39. That is 2 2/39. What do you think? Good stuff? Come on. Okay. I realize that 3 hours of math in one sitting is kind of the equivalent of toothpicks under the fingernails. I used to do everything I could to keep lecturing till 8 o'clock at night, but usually somewhere around 7:30 I look out and I see that no vacancy sign across everybody's forehead. So I do try to keep it short and give you work time. So what I'll do is I'm going to try to be done, looks like probably by 7:20 or 7:30 tonight, just so I don't burn you out on the first night. And I'll give you time, if you want to use the computer lab next door and try to sign up for my math lab, you can. Or if you just want to get going and recover and tackle more of this tomorrow, you can as well. So let's move on to our last little piece for the night. One of our last little pieces. Decimals. Decimals are actually somewhat simple to deal with. If I give you 0.21, what's the formal way of pronouncing that? Do 21 hundredths. And when you write it out that way, you can see that there's the count and the name. If I were to try to add like 0.21 plus 0.3, would it look like this? What's wrong with that? Zeros don't line up. Do they have to?
Yeah.
Why? Yeah, the 4th grade teacher told us that at some point, right? You gotta line up that decimal point. Like that. Well, the reason why is this is 21 hundredths. This is 3/10. They have different names. If I put the 0 there, that now becomes 30 hundredths. Or the other way to look at it is that 3/10 here can only combine with the 2/10. Lining up the decimal points is nothing more than lining up the digits with the same place value. because when we add or subtract, we can only combine digits that have the same name or same place value. Normally, we'll fill in a 0 there. Now, 1 and 0 is 0, or 1. 2 and 3 is 5. What do we do with the decimal point? It comes straight down. Again, when we add numbers, we keep the same name. 21 hundredths plus 30 hundredths better be 51 hundredths. If we're subtracting, it follows the same pattern. We have to line up that decimal point again because we can only combine digits that have the same place value. Now here again, we have to put in a 0 to line it up. And we're going to borrow just like we did with whole numbers. 0 minus 2 doesn't work, so we got to borrow from the 8. That's 7 and 10. 10 minus 2 is 8. 7 minus 5, 2. 3 minus 4 can't work, so we borrow from the 7. We ignore the decimal point there. This is 6 and 13. 13 minus 4, 9. The decimal point does still come straight down. We can't cross it without bringing it down. 6 minus 2 is 4. I'm going to show you another one here just because this one gets a little tricky for people. So I'm like 8 minus 3.9476. Where's the decimal point on the 8? Right at the end of it. So that's what we have to line up. So obviously here we have several zeros that we have to fill in. 4 of them, in fact. We go to subtract, we're going to borrow. 0 minus 6 can't be done. We're going to borrow from here. But that's a 0. There's nothing to borrow. We have to go back down here and find until we find something to borrow from, which is the 8. So that'll be a 7. But what we borrowed there has to go here. This is 10. We need it down here, so we have to keep going. So that's 9. This is now a 10. That's a 9. This is now a 10. Borrow again. That's a 9, and this is now a 10. And now we're all set to subtract. 10 minus 6, 4. 9 minus 7, 2. 9 minus 4, 5. 9 minus 9, 0. Decimal point comes down. 7 minus 3 is 4. Questions? Okay. Multiplying. Do I have to worry about lining up the decimal points if I multiply those? No, I don't. Because when I multiply, I don't need the same name. 21 times 3 is 63. Where does my decimal point go? 3 spaces over. I have to add a 0 and put the decimal point in there. Why? Well, we've been taught you have to count 1, 2, 3 decimal places in the problem. 1, 2, 3 decimal places in the answer. Why? 4th grade teacher, right? Well, this is 21 thousandths. This is 3 tenths. We combine the counts. 21 times 3 is 63. Or not thousands, this is hundreds, sorry. Hundredths times tenths is thousandths. Had the thousandths just in the wrong place. There we go. Make sense? I'm starting to get tired and not make so much sense myself. I'm sorry. So we've talked about fractions and decimals. Let's look now at converting between them. We're going to take a little step back, and we're going to look at the structure of the decimals. To do that, we're going to start out by looking at our place values again. This is the ones place, tens, hundreds, 1,000s, 10,000s, 100,000s, and so on. We notice a pattern here. Every time we move one place value to the right, what happens to the value? It's divided by 10. It decreases, divided by 10. So if we were to keep going over here, 1 divided by 10 would be 1/10. Divide by 10 again, 1 100th, 1 1,000th. The place values continue to follow the pattern. Now you might be looking at those place values thinking those look suspiciously like fractions, because they are. Decimals are nothing more than a short way of writing common fractions. 0.7 is really just 7/10 as a fraction. So it's really simple to convert a decimal into a fraction. If we have 0.38, well, this is 38 hundredths. The last digit is in the hundredths place. So right, it is 38 over 100, and of course we would reduce that. What can both of those be divided by? 2. Here's 19/50ths. If there's a whole number in front, like 13.65, what do we do with it? Well, the answer is we do absolutely nothing with the whole number. That's 13. The 0.65 is 65 hundredths. And of course that can be reduced by 5. So that's 13 20ths. Don't forget there's still that 13 in there. So 13 and 13 20ths. What do you think? Better than a sharp stick in the eye? Waiting for it? Okay. Going from a fraction back into the decimal is actually quite easy. 3/4. This fraction bar here that separates the numerator and denominator of a fraction not only can mean a fraction, but it can also mean division. So a division problem can be thought of as a fraction, and a fraction can be thought of as a division problem. 3/4 can be thought of as simply 3 divided by 4. Well, 3 divided by 4 is 0.75. You can either use the calculator or you can use fractional division, which is our next thing to look at here. How do we divide a number that's smaller than what we're dividing it by? Like 2/5. Well, it's 2 divided by 5. Does 5 go into 2? No, it doesn't. So we leave it blank or put a 0 above it. We move on to the next digit. The only problem is here there's not a next digit. So we put in our decimal point and we can add a 0. Does 5 go into 20? Sure does. That's 4. Now when we added the decimal point here, we had to put it up here as well. So that is 0.4. So 2 divided by 5 is 0.4. 2/5 is the same as 0.4. Let's do 3/7. So we're going to do 3 divided by 7. Does 7 go into 3? No. We're going to add the decimal point and then add a 0. Does 7 go into 30? Sure, 4 times. That's 28. 2. We can keep adding zeros. We add another 0 and bring it down. 7 into 20. Twice. That's 14 with 6 left over. We can add another 0. 7 into 60. 8 times. That's 56. Well, this is going to go for a while. How do we know where to stop? Well, let's say that you're told you want this to the nearest 1,000. We're at the nearest, we're at 1,000. Can we stop there? No. Add another 0. We subtract this to get 4. Adding another 0 makes it 40. 7 into 40 is 5 times. We had to go that one more place because this 5 tells us that when we round that to the nearest 1,000, instead of being 0.428, it has to round up to 0.429. Any questions? Okay. I want to start this a little bit this week. We'll talk about it a little bit more at the beginning of class next week. But what happens when we have problems like this? Well, looking at that, there are several ways that that could make sense. Some might look at it and say, oh, I'm going to do the 5 plus 2 is 7, 3 minus 1 is 2, 7 times 2 is 14. That kind of makes sense, but it's wrong. How are we supposed to do that? Order of operations. We have to multiply first. 2 times 3 is 6. And then we can do the other operations. 5 plus 6 is 11, minus 1 is 10. In math, whenever there's more than one operation in the same problem and there's nothing to tell us what has to happen first, normally in real life there's a story that goes with the problem and that tells us what has to happen first. But if you just run into operations like this with nothing, no context to tell us what's going on, order of operations applies. An order of operations is actually a 4-level system. On the first level, the first thing that has to be done, or has to be accounted for, is enclosing symbols. Now, many of you were taught that these are just parentheses. And parentheses is a single type of enclosing symbol, but there are others that we'll encounter. Second thing that needs to be done is exponents. These are two things. There's powers and there are roots. Next is multiplication and division. Those, again, we said that they're the same operation, just one's forward, one's reverse, so they happen at the same time. And then the last thing would be addition and subtraction. Again, they're the same operation, they happen at the same time. So let's take a problem a little bit more difficult than the one we had here. There, just a little bit more difficult. Now, I'll tell you this. Most people are really, really tempted. Hey, 5 plus 2 is 7. Let's do that and get it done with. No. Can't do that. This 2 is multiplying that parentheses. That multiplication has to happen before that addition. That addition is one of the last things that can happen in this problem. Order of operations, first step is enclosing symbols. Do we have any? Right there, we got parentheses. So we got to start inside those parentheses. Inside those parentheses, the order of operations still applies. Are there any other enclosing symbols? No. So we moved on to the next one. Exponents, powers or roots. Yeah, right there, 3 squared. 3 to the second power is 9. So nothing else changes. I just replaced that 3 to the second power with a 9. Next, any other powers or roots? No, so multiplication and division. Well, we've got a division, a multiplication, and a division. So there's several of them there. How do we know which one to do first? We go left to right. Just like if there's more than one thing that's on the same level, we go left to right. So we're going to do this one first. 24 divided by 6 is 4. A lot of writing in these problems. Next, we're going to do the 2 times 3, which is 6. Nothing else changes. And then 6 divided by 6, right, which is 1. And then we're done. Multiplication, division. Next level, addition and subtraction. Well, it's all addition and subtraction left, so we're just going to go left to right. 8 minus 4 is 4. Four plus 9 is 13. Now, a lot of people at this point say, well, can't you do minus 1 plus 1, just cancel it out? Well, in this case, it would work, but sometimes it doesn't, so you got to be careful. 13 minus 1 is 12. 12 plus 1 is 13. Now we've reduced everything in the parentheses to a single number. So now we don't need that enclosing symbol anymore. We can take it out. What do we have to put in here, though, when we take out that parentheses? There was the 2 here with no symbol between it and the parentheses. We have to put in multiplication there. It's implied to be multiplication. So now we have to do the 2 times 13, which is 26. And 5 plus 26 is 31. As I said, adding that 5 to anything is the last thing done in the problem. A lot of people do it first, and they make a mistake before they hardly even get started. How about this one? To understand this one, we need to understand this thing here. We just said what it was a little while ago. What is it? It's division. It's a fraction bar. And it does mean division, but it is also an enclosing symbol. It is separating the top of the problem from the bottom. It's telling us we have to do everything on top here first. Start out with the 7 times 9 is 63. 4 times 3 is 12. 63 minus 12 is 51. Then we have to do everything on bottom. What do we do first? 5 squared is 25. And then 24 divided by 3 is 8. 25 minus 8 is 17. So the top is 51, the bottom is 17. Now we divide to get 3. What do you think? Pretty awesome. Need to rush home and do something right now. Actually, your kids are sick. You want to stay here and get into the computer lab and do something, don't you? Hopefully it's something when you get home. The kids are the wife. In my math lab, there's homework 1 that'll be due. It'll actually be due, at, I believe, at 6 o'clock next Tuesday. So that doesn't give you really any time to finish it up after once you get start class. But again, if you have questions, use the hints or use the Ask My Instructor if you have questions, and I'll help you out. First one's pretty straightforward. It is kind of long. It's like 51 questions or something like that, but they're pretty quick questions. With that, I'll let you guys have the rest of the time. If you want to go next door in the computer lab,